right, so here is the second lecture for these virtual online classes. So continuing what we did last class, dealing with pumps, now also dealing with piping systems. So one more thing we want to talk about in terms of the pumps before we go into this whole system is something called the net positive suction head required. So NPSH subscript R, net positive suction head. So guys, basically the difference between the total pressure at the pump suction or the inlet nozzle and the vapor pressure of the fluid. And so my pressure at the suction part, PS, minus the vapor pressure of the fluid, PV. This is important because it basically tells us when cavitation may be an issue. So cavitation happens if the pressure in the fluid is lower than its vapor pressure. If the pressure is lower than the vapor pressure, some of that fluid or liquid is going to turn into a gas. And that's what cavitation is. And that's not good for pumps. So generally, as I mentioned last class, to move a liquid, you generally deal with a pump. To move a gas, you deal with something like a fan or a blower. So not a pump, basically. And so pumps ends up having major problems if those liquids turn to gases. So we want to avoid this cavitation happening. So we want to avoid having a pressure at the inlet less than pressure of the vapor pressure of the liquid itself. And so we want to make sure that our net positive suction head doesn't let that happen. So cavitation, when it comes to pumps, is bad, not only for the efficiency, but also it can actually cause damage to the pump itself. And so therefore, where we place the pump in a system is actually very important in terms of, do I place it before this component or after this component, can actually make a big difference in terms of that net positive suction head, and therefore could have some issues regarding cavitation. So we see here in this figure, have water vapor pressure based on temperature. So that vapor pressure changes with temperature. Either you use units of standard PSI, absolute, or they also have in terms of feet of water, so like a head value. So as I mentioned, if you place the pump where the net positive suction head available is greater than the required net positive suction head, so each pump will have its own sort of net positive suction head required. It says I need this much to make sure that I avoid cavitation. So you just want to make sure the net positive suction head at the location you plan on putting it in your system. So for example, this system down here, I'm placing a pump here. I want to make sure at this location right here, my net positive suction head is larger than the required value given by the pump manufacturer. So to find this net positive suction head available at this point, essentially I'm just doing the flow through pipes that we saw last week. I basically just using the standard energy or Bernoulli equation, net positive suction head available. I have some pressure at the location, have some velocity at the location, have some head loss at the location, have some height at the location minus the head loss. And then I also want to make sure that I'm above, after I do all that, I'm above the vapor pressure. So add on another vapor pressure term. So very similar to what we did with Bernoulli or the full energy equation, we tack on this extra part to make sure that we are above that vapor pressure condition. So basically, again, just figure out here what sort of net positive suction head we have, take away the vapor pressure, and that's hopefully larger than NPSHR from the manufacturer. So probably best way to see this is using an example. So have a system here, have a pump, that's at location 2. So this pump here, I want it to deliver 2 cubic feet per second of 80-degree Fahrenheit water. Intake pipe diameter here is 8 inches. This is 6 feet above the surface of the water, so 6 feet height difference between where the pump's located and the surface of the water. I want to know the net positive suction head for these conditions. So assuming my total length of pipe is 10 feet, both the bend and entrance down here both have minor loss coefficients of 0.2, so 0.2 for the bend and 0.2 for the entrance condition. find that net positive suction head. So basically at the entrance of the pipe, see what sort of pressure I can develop or pressure I have there, and compare that to any requirement that might be important for this certain pump. So to do this guy, again, I want to write the energy equation or Bernoulli's equation between the water surface, which is 0.1, and the pipe inlet, which is 0.2. So standard Bernoulli equation, P1 over gamma, V1 squared over 2G plus Z1 is P2 over gamma, V2 squared over 2G plus Z2 plus my head losses. And then in terms of the pressures, pressure 1 at the reservoir surface is atmospheric pressure. Atmospheric pressure is 2,116 pounds per square foot. The water surface velocity is essentially 0. So I'm pumping this water out of this big, large pool. And as I'm pumping it out, the pool level is moving down very, very, very slowly. So I can basically call V1 0. In terms of my heights, the Z's, I can call Z whatever I want. So I'm going to call the water surface down there Z1, which makes Z2 6 feet because my pump is 6 feet higher than the water surface. And then my velocity going through the pipe, I can just find that from the flow rate. So flow rate divided by area is velocity. Area is pi d squared over 4. And so I have a flow rate of 2 cubic feet per second, a diameter of 8 inches, want to make that into feet. So plugging that all in for my velocity gives me a velocity of 5.73 feet per second for this flow rate. And then the last thing I need in my equation is the head loss. So a head loss, I'm going to have a combination of major losses. So this is through my 10 feet of straight pipe. And then I have my minor losses, those two values from the entrance and from the bend itself. So plugging all those values basically into this equation up here, a lot of stuff on the left-hand side is going to go away. So V1 is going to go away, Z1 is going to go away. V2, I know from down here, C2 is just 6 feet. Then HL is going to become all this stuff. Another important thing about this is my head loss happens through my pipe. So in my pipe, I'm dealing with V2 because that's the velocity through my pipes. So in that equation for the head loss, I have a friction factor F. So I need to find that friction factor. And to do that, I need the Reynolds number and the relative pipe roughness. So again, going back to either fluid class or first week of this class, I have a Reynolds number, again, based on flow rate. So 4 times Q over pi d and kinematic viscosity for the water. So 4 times my flow rate of Q2 cubic feet per second. Pi times the diameter, which is 8 divided by 12, because that's in feet. And then kinematic viscosity of water, I'm going to have to basically look that up in a table. So at 80 degrees Fahrenheit, which is what this was for, I have a kinematic viscosity of 9.3 times 10 to the negative 6 feet squared per second for that. So my Reynolds number in this case is 411,000. And then relative roughness parameter, in the question it said that I could assume this was a smooth pipe. So for smooth pipes, epsilon value is 0. So epsilon over d also 0. And then I need to find the friction factor by using either the Moody chart or those equations that we saw again in the first week of class. And doing either of those, I find my friction factor is 0.0136. So then looking at the equation that I'm left with, I have P2 over gamma, the only thing left on the left-hand side, equals P1 over gamma minus V2 squared over 2G minus Z2 minus this head loss term, which I can write as FL over D plus K, V2 squared over 2G. But then I already have a V2 squared here, so I can pull that basically into this term here, and that's where this 1 comes from. And then the other thing I want to have for my net positive suction head is to take away the vapor pressure of water. So I can look at the figure way back on slide 2, vapor pressure of water at 80 degrees Fahrenheit. Here we have 80 degrees Fahrenheit, vapor pressure of water right here. Gives me roughly 0.5 psi. You can also look that up in a table for more accurate values. That's where I got this from. So 0.506 psi for water at 80 degrees Fahrenheit. So I want, as I said, tack that onto the left-hand side. So minus PV over gamma to give me the net positive suction head at this location. So there's my equation again. Now it's just a matter of plugging all the values in. So I always want absolute pressures. So absolute atmospheric pressure, 2,116 psf. Gamma for water, 62.4 pounds per cubic foot. The vapor pressure is 0.506 psi. But again, I want PSF, so everything converted to feet. So multiply that by 144. Then again, divide it by the specific weight of water, 62.4 pounds per cubic feet. I'm going up 6 feet, so take that away. And then here I have 1 plus 0.0136 for F, length of 10 feet, diameter of 8 divided by 12, again in feet. And then for my K values, I have 1 entrance and 1 bend, both assumed to be 0.2 for the K values. V squared, 5.73 feet per second, divided by 2G, 2 times 32.2, gives me a grand total net positive suction head available at that point of 25.9 feet. Now normally, if I have a typical single stage centrifugal pump, intake diameter of 8 inches, pumping 2 cubic feet per second, critical NPSH or NPSH required is generally somewhere in the neighborhood of 10 feet. So this having an available net positive suction head of 25 or almost 26 feet is well above that required value of 10 feet. And so therefore, I shouldn't have any problems with cavitation in this example. If I had ended up with an NPSH less than 10, then that would be an issue, and that would not be a good place to put this pump. But since I have an NPSH that's well above the required value, this is definitely a good location to put the pump. So next up, we have piping and instrumentation diagrams. So these are obviously a widely used drawing in the design package. They identify all process components, including equipment, lines, instruments, valves, and connectors. They illustrate the basic control philosophy, showing sensors, transmitters, controllers, control elements, form the basis for bills of materials and other lists, used by process hazard assessment team to evaluate safety of the process and whether additional safeguards are needed for doing the actual construction. So it's a little bit different than the process flow diagram. Process flow diagram basically shows you what, where, and how these fluids are being manipulated, whereas a piping and instrumentation diagram gives you the parts list, basic methodology for the hardware and software that's going to control and facilitate what's actually happening with the fluid flow. Then pump selection, so I need to figure out obviously what pump to use. And so that's going to be one of the last steps in this thermal design process, because generally the piping system is also one of the last steps. You need to figure out where fluid needs to go. And so you need to lay out a whole bunch of piping network to figure that out. And then once you have that piping network in place, you need to figure out, okay, how am I actually going to get this fluid there? And that generally involves pumping systems. So where am I going to place my pumps in this whole piping network to actually make this work, give me the right flow rates, make things go where I want them to go. So obviously I need to have all the heat material balance completed, all the major equipment sized and selected in place, so I know, again, what sort of pressure differences I'm dealing with, and how many or how big of pumps I'm going to need. All my piping system, I'm going to need a bunch of head losses for that. And obviously economic considerations are important, and so I need to figure out kind of how to do this for the least amount of money. The general cost estimates for piping systems and pumps usually have rate structures, or sorry, utility rate structures are all major influences. So how much energy cost is also going to be important for this as well. So just in terms of the hardware, typical values and purchase values for the purchase and installation of Schedule 40 commercial steel piping shown in this table here. So based on diameter, the larger diameter obviously is going to have more cost per foot, but at the same time, you'll be able to move more fluid through there more easily. So this is just values for purchase and installation. Doesn't include other things associated with the piping network, like the purchase of land, any sort of trenching, you need to bury these pipes, backfilling, disposal of old systems. So this is just straight up for the new set of pipes as well as their installation. In addition to the pipes, you also need pump costs. Pump costs are going to vary a bit more than this. Order of magnitude estimate given by this expression here, where the cost in dollars is 10,000 times the square root of horsepower over 130. So horsepower being the pump output in horsepower. So you can kind of give, again, an order of magnitude estimate for the cost of the pipe, or sorry, of the pump. Again, not necessarily a very accurate number, but just more of a order of magnitude estimate. So another thing that we can see from the previous table, as I said, is that as the pipe diameter increases, I have a larger cost associated with it. But on the other hand, if I have a larger diameter pipe, that's going to have less friction involved with it, less head loss involved with it, and therefore less power associated with having to get the fluid through there. And so you have to kind of look at two things, the lifetime energy cost and the lifetime material cost. And so my lifetime energy cost, as the pipe diameter increases, is also going to decrease because, as I said, larger diameter, less friction, easier to get it through there, so less energy as I go up. But as we saw from the table before, as pipe diameter goes up, this green line is my material cost, and the material of larger diameter pipes costs more, as we can see. And so proper sizing of the pump and piping network generally involves an iterative process. You need to kind of make a first guess as to how much fluid is going to be moving through there, because that's what the friction factors and head loss all depend on. And so you have to have baseline values of those. And then from that, you can find a pump that will accomplish what you need in terms of flow rate. But what we really want to look at is the combined lifetime costs. So both the energy and material kind of put together. So basically these two curves, green and blue curves added together, give us the red curve. And this red curve is really what indicates the overall cost in terms of pipe diameter. And you can see that has a fairly substantial minimum right here. And so that's going to be kind of the most effective, most cost-effective region in terms of my piping network. So I want to look at somewhere in the neighborhood of this diameter pipe to minimize the overall lifetime cost of the system. And last thing, as mentioned, piping design process is generally iterative. Generally have to start with some initial estimate of the pipe diameter based on some general fluid velocity. And so general fluid velocity recommended values, if you're dealing with a liquid, somewhere in the neighborhood of 2 meters per second. If you're dealing with gases, somewhere in the neighborhood of 10 meters per second. That can provide you with initial estimates to give you initial pipe diameter, to give you initial pumps and all that sort of stuff. And then you can go back and refine that iteratively over and over again to get your final values. So that is it for today. That is everything to do with pumps and pump and piping systems. That should get you through homework 3. And so that is the end of that section of the course. Next lecture, we'll start to deal with turbo machines and turbo machinery, section 4 of this class, essentially. So we'll see you then.